Hello, everyone, and welcome to this AP Chemistry virtual lesson. My name is Michael Faribaugh, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Today, we are going to continue our discussion of Unit 7, Equilibrium. So in yesterday's lesson, Mr. Byrne talked about a variety of concepts involving equilibrium, and we'll continue that today. Just to remind you, you can go to apstudents.org/exams2020 to get updates and information about taking AP exams online this year. Remember that your AP chemistry exam will be given on May 14th, and there are 2 free response questions. So again, this is information about when to take the exam, but again, feel free to go to apstudents.org/exams2020 to get updated information. Hopefully you have access to a periodic table and some scratch paper and something to write with. In today's lesson, we'll be talking about Unit 7, and so topics 7.7, calculating equilibrium concentrations, and 7.8, representations of equilibrium, introduction to Le Chatelier's principle, and the reaction quotient. And again, you can see both the topics and the science practices involved. So things like representing visually the relationship between the structures and interactions across multiple levels. So we'll definitely see particle diagrams today. And again, with Le Chatelier's principle, explaining the connection between experimental results and chemical concepts, processes, and theories. So again, we'll talk about R.I.C.E tables and calculating equilibrium concentrations, the reaction quotient, and Le Chatelier's principle, as well as particle diagrams. In yesterday's lesson, Mr. Byrne had presented you some questions related to equilibrium. So here we have an equilibrium involving the reactants X and Y, and then the product XY. And so a student made a claim that according to the information in this diagram, you can see we have A, B, C, and D. So down here at the bottom on the X-axis, we have different points in time. So the student made the claim that at time A, equilibrium was going to be reached because the concentration of X and XY were almost the same. So they were focusing on this particular point in the diagram. Well, hopefully you understand that equilibrium has to do with the concentrations or the pressures not changing over time. So we would disagree with this claim. Equilibrium is going to be first achieved right around here at point C, because from this point onward, you can see that the concentrations or the pressures of the reactants and the products no longer change over time. But the concentration of a reactant does not need to be the same as the concentration of a product. So equilibrium does not mean equal in terms of amount of reactants and products. It simply means that those concentrations are not changing because the rate of the forward reaction is equal to the rate of the reverse reaction. In the other question that was asked to you in the lesson yesterday, we have an equimolar mixture of X and Y. So at time 0, and you can see here in this first diagram, we have 1, 2, 3, 4, 5, 6, 7 atoms or molecules of X, and then we have 1, 2, 3, 4, 5, 6, 7. So again, that would be equal molar of X and Y. Now, if you look over time, what is happening is we're starting to form molecules of XY. So there are an increasing amount of molecules of XY, and as a result, the concentration or the amount of X and Y is going down. So now we get to this point at 300 seconds. We have 1, 2, 3, 4 molecules, 5 molecules of XY, and then we have 2 atoms or molecules, I guess, depending on what the substance is, we have atoms of X and Y. So draw a particle picture in the box for time equals 400 seconds that is consistent with the conclusion that equilibrium was reached. So equilibrium was reached at some point between 300 and 400 seconds. So what I have chosen to do in my particle diagram is to show that if equilibrium has been reached, then the concentration should not be changing. So therefore, I have essentially copied the exact same particle diagram that we have at 300 seconds. So therefore, we know that equilibrium has been reached when the concentrations of reactants and products are no longer changing. All right, other question that was asked for your homework in yesterday's lesson. It says that we have an equilibrium between nitrogen and oxygen and nitrogen monoxide. So we have N2 plus O2, and it produces 2 molecules of NO. It says, write the expression for the equilibrium constant. Now, I'm going to show you 2 different equilibrium constants. One of them has brackets, and the other has parentheses involving the letter P, where P stands for pressure. So you have to read this question carefully, because it says to write the expression for Kp. This is what the question was looking for, not the Kc. So it'd be a shame for a relatively easy question for a student to miss because they weren't paying attention to the difference between brackets, which means concentration, and P for pressure. Now, had you done the following, had you written Kp like this, so NO squared over N2 and O2, this would not have earned the point because the readers would not see the letter P indicating pressure. So parentheses is not the most important part here. It's the fact that you have P for pressure. Now, we've seen lots of strange answers on the AP chemistry exam for questions like this. I'll show you an example of a rather strange one, and I would think this would still earn credit, but just, again, try to be careful with your symbols. So I've seen students do things like this. So they're writing the pressure of the NO and the pressure of the O2. So that subscript is still present, although it's outside the parentheses. I think this would be fine. I would still give that student credit because it's clear that they understand P for pressure and they have the appropriate squared symbol there in the exponent. So that's a little bit different than what I'm showing you on the screen, but that would consider to be correct. But just watch out for the fact that Kp involves pressure and Kc involves concentration. All right, the next part is going to involve what I call a R.I.C.E table. So we're going to use R, that stands for reaction, and then I is the initial amount, C is going to be the change, and then E is what happens at equilibrium. So a student injects nitrogen and oxygen into a previously evacuated rigid vessel. So the pressure inside the container was 0 initially, and now we have a pressure of nitrogen, which is 6.01 atmospheres. So we're being given that information. And then the pressure of oxygen is listed as 1.61 atmospheres, but that's it. So initially there is no nitrogen monoxide. This reaction will proceed toward equilibrium by shifting from left to right. In other words, the concentration or the pressure of nitrogen will go down by a certain quantity X. Because there is a 1-to-1 mole ratio between the nitrogen and the oxygen, the concentration or the pressure of O2 will also go down by X. But since there is a 2 as the coefficient for the NO, then the increase in pressure for the NO would be 2X, since 2 moles of NO are formed for every 1 mole of O2 or N2 that is consumed. So at equilibrium, we have 6.01 minus X for N2, we have 1.61 minus X for O2, and we have 2X for the final pressure of the NO. Now we are told that the partial pressure of the NO at equilibrium is 0.122 atmospheres. So now we can solve for X. So 2X equals 0.122, X equals 0.061. So on your calculator, if you do 6.01 minus 0.061. In other words, if you do this math, substituting in the value of X, you get 5.95. I'm just using 2 decimal places for my pressures. If you do 1.61 minus 0.061 on your calculator, you will get 1.55, again, rounding off to 2 decimal places. And again, if I look at these three values, I can take these three pressures and I can plug them in to the KP expression, the expression that we wrote in part A, because now I have to calculate the value of KP. So we had to figure out the final pressure of each substance at equilibrium, and we can now plug those values in to the KP expression. So 0.122 squared divided by the product of 5.95 and 1.55 gives us our answer. So KP works out to be 0.00161. Okay, well, those were the answers, are the answers to the homework from yesterday's lesson. So now we're going to focus on R.I.C.E tables and calculating equilibrium concentrations. So I have an equation involving hydrogen reacting with iodine to produce hydrogen iodide, and this is in the gas phase. Suppose that we are given that at equilibrium, the concentration of hydrogen is 0.1 molar, the concentration of iodine is also 0.1 molar, and the concentration of HI is 0.714 molar. If we had to calculate the value of Kc with these numbers, just plug them in to the K expression. So you have hydrogen iodide on top, that would be squared because of the coefficient. And then we have hydrogen and iodine on the bottom, so we just plug in our numbers. And if you do this math on your calculator, 0.714 squared divided by 0.1 squared, you get 51.0. So R.I.C.E tables are going to be used if we are trying to find the final concentration of each substance. Now that we know the value of K, we can set up a R.I.C.E table for a new problem. A sample of hydrogen and iodine is added to a previously evacuated reaction vessel. The initial concentrations are hydrogen equals iodine equals 2 molar. Calculate the concentration of all three gases in the reaction vessel at equilibrium. So we start with concentrations of 2 molar for each reactant and then 0 for the product. Well, of course, because we have 0 product, we're going to have to shift this equilibrium position will shift toward the right in order to reach equilibrium. So the concentration of hydrogen goes down by X, concentration of iodine goes down by X, and because of the 2 as the coefficient, the concentration of HI goes up by 2X. Notice that in the change portion of this table, so when you are writing your X's, the change in X needs to be proportional to the coefficients. So we're going to get 2 minus X, and 2X. So just a comment, there is no such thing as the law of conservation of moles. A student might be thinking that somehow the change in X has to be the same on both sides of the equation, but there is no such thing as the law of conservation of moles. It just so happens that coincidentally, we have equal number of moles of gas on each side of this particular equation, but suppose we had an equation involving 3 moles of hydrogen reacting with 1 mole of nitrogen to produce 2 moles of ammonia, NH3. Notice that the change in X does not have to be equal on both sides of the equation. So do not think that somehow the X's you have on the left that are lost have to equal the X's on the other side that are gained. It was just a coincidence in this particular example that I'm using. Okay, so we're going to plug in the final row of the R.I.C.E table in terms of X into the equilibrium constant expression, and we know that Kc equals 51. So now we can solve for X. And I will tell you that on the AP Chemistry exam, you do not need to use the quadratic equation. So therefore, I am using an example in which you can just do simple algebra. The fact that I have a perfect square on the top and the bottom means I can take the square root of both sides and avoid any complicated math or the quadratic equation. So when I take the square root of both sides, I get 2x over 2 minus x equals the square root of 51, which works out to be 7.14. Now let's go ahead and continue solving for x so we can figure out the final concentration of each chemical at equilibrium. So we'll go ahead and multiply both sides by 2 minus x. Then we'll distribute on the right. And then we'll combine like terms. So we get a total of 9.14x equals 14.28. And we solve for x, we get 1.56. So I can now plug in x into my final row of my R.I.C.E table. So 2 minus 1.56 equals 0.44. And then 2 times x equals 3.12. Now, to show this graphically, like the diagram that was presented earlier from the homework problem, we start with 2 molar for hydrogen and iodine, and then that concentration decreases over time to a final value of 0.44. We start with 0 for our concentration of the product, HI, and that rises to a final concentration of 3.12. Now, if you had to label where exactly on this curve is equilibrium achieved, at what point in time, it's not when the concentration of reactants and products are equal. It's when the concentration of reactants and products no longer change over time. So from that point on, equilibrium is reached because the concentrations are holding steady. Okay, so in that example, we started with reactants only. Here is an example, same system. Let's start with product only and watch what happens. So we're going to start with 3 molar HI. So we have 0 for the concentration of hydrogen and iodine, the reactants, and we have a concentration of 3 molar. So you'll see a similar pattern. We're going to do minus x and plus x. But if we're going from right to left, it's going to have to be minus for the product and plus for the reactant. So it's going to be plus x for the reactant because we had none to start with, and then minus 2x. Again, remember that the change is proportional to the moles from the coefficients. We're going to plug these numbers into the K expression like we did before and solve for x. Now, if I'm going too fast, feel free to pause the video because I am kind of, trying to cover a relatively large amount of material in a relatively short amount of time. So feel free to pause the video if you need to process all of the calculations that I'm doing for you. All right, I'm going to take the square root of both sides. So 3 minus 2x over x equals 7.14. Now we're going to solve for x. So we get 9.14x equals 3. X is 0.33. Let's put that into the values for the final row of our R.I.C.E table, 0.33, and 3 minus 0.66 is 2.34. So now in this example, again, graphically, we started with all products and no reactants. So the reactants increased from 0 to 0.33, and the product decreased from 3 to 2.34. As you can tell, equilibrium was achieved at this point when the concentration of reactants and products were not changing. All right, well, here's a third example. What if I start with a mixture of both reactants and products? So my concentration of HI is 3 molar, and my concentration of H2 and I2 is 1 molar. It was obvious in previous examples that I was either going to proceed to the left or to the right. Now it's actually not so clear. If I'm going to reach equilibrium, how do I know whether I'm going to have the reactants go down or the products go down? So it's going to be a little confusing here. This brings us to another topic, another concept, which is called the reaction quotient. Okay, imagine that you were at a mall or a shopping center and you see a map and you're trying to figure out where you would like to go to get to a particular store. Well, there's a particular part of the map that you're looking for, and that is where you are right now. Essentially, that's what the reaction quotient is. The reaction quotient is kind of a "you are here" symbol because it tells you where you are now and what needs to happen in order to get to equilibrium. So suppose you have a flask that contains a certain amount of reactants and products. This is your reaction vessel. Well, this is where you are now, and at some point, the system will eventually reach equilibrium. So Q, the reaction quotient, it looks identical to the equilibrium constant expression. So these two look identical. The difference between Q and K is that with Q, you just plug in the values for what you have right now. And once you plug in the values for what you have right now, then you can compare the value of Q with the value of K, and then determine in which direction you must proceed in order to reach equilibrium. So we're going to compare Q with K, and there are three possibilities. Okay, so the Q is where you are right now. The three possibilities are the following. Either Q equals K, which means you already are at equilibrium, so it's already arrived. But if for some reason Q is less than K, remember, this is products over reactants. So if Q is smaller than K, it means you either have too many reactants or not enough products. The reaction would then proceed from left to right in order to reach equilibrium. But if, on the other hand, Q is somehow greater than K, then the reaction indicates you have too many products or not enough reactants, and you would have to proceed from right to left. So comparing Q with K, this is a way of remembering it. I like this little mnemonic. This is a little memory device. So what I've done is I'm comparing Q with K, but I put K first, and there's a reason for that. You'll see in just a moment. So if K equals Q or Q equals K, you already are at equilibrium. Now, if Q is less than K, the reaction would have to proceed from left to right. And if Q is greater than K, then the reaction would proceed from right to left. So here's the little memory trick. Because I've done it this way, watch what happens. Look at that less than symbol. Q is less than K. It also indicates the arrow that the reaction would have to proceed from left to right. It's a little trick. If you write it this way with K first and Q second, it's kind of a little cheat sheet for yourself because it shows you that you can kind of make an arrow out of the inequality symbol, okay? So if Q is less than K, you're going to go toward the products. And if Q is greater than K, you're going to go toward the reactants. Okay, well, we have 3, 1, and 1. Let's go ahead and plug in the values that we have now and see where we are relative to K, which is 51. Well, we're going to plug them in. We have 3 squared divided by 1 times 1, that's 9. And since 9 is less than 51, that means that Q is less than K. The reaction would proceed from left to right toward the products. So the reactants are going to go down by X, and the product is going to go up by 2X. Again, that's the change based on the mole ratio and the coefficients. 1 minus X, and 3 plus 2X. Let's go ahead and plug this in, solve for X. So we'll do this math. We're going to take the square root of both sides, and then we're going to simplify the expression. And then once we simplify this expression and we solve for X, in this case, X works out to be 0.45. So 1 minus 0.45 is 0.55, and 3 plus 2X, which is 3 plus 0.9 is 3.9. So here we had a mixture of reactants and products. And since it was shifting, proceeding toward the right, the products increased to a final amount of 3.9, and the reactants decreased to a final value of 0.55. So in looking at equilibrium in 3 different examples here, you can see that we started with either all reactants. Now watch what happens when I plug these numbers in, 0.44 and 3.12, I get a K value of approximately 50, 50.3. That's close enough to 51, that's sort of approximately equal to K. If I started with only products and no reactants, I got a different set of numbers, but when I plugged them into the K expression, I still got the same value of K. And in our last example, I had a mixture of reactants and products, so we got a different set of values, but when I plugged them into the K expression, I got the same value. So look at that. Look at the fact that I started with either all reactants or all products or a mixture of reactants and products, and I still achieved the same equilibrium constant. The only way you can change the value of the equilibrium constant is to change the temperature, which we're going to see a little bit later in this lesson. All right, here we have a discussion of Le Châtelier's principle, and I'm using a different equilibrium system. This involves nitrogen dioxide reacting to form dinitrogen tetroxide. It turns out that NO2 happens to be a brown gas, and N2O4 happens to be a colorless gas. So if you have an excess of NO2, then your mixture will look sort of a reddish brown. And if you have an excess of the N2O4, it's going to be sort of a lighter shade. So that color change indicates you either have more of the reactants or more of the products. Suppose that a chemical reaction has already reached equilibrium, okay? Now suppose that the rate of the forward reaction, which is equal to the rate of the reverse reaction, you're at equilibrium, and the concentration or the partial pressure of each reactant and product are no longer changing over time. What would happen if a system that's at equilibrium experiences some sort of stress? Now, that is what Le Chatelier's principle is all about. If a system that's at equilibrium is perturbed or experiences an external stress, then the position of the equilibrium may experience a shift, and the shift is in the direction that will somehow relieve that stress. So what exactly are we talking about when we say a stress? Either a change in concentration or pressure or temperature. Now remember that when Q equals K, the system is at equilibrium. So if the stress occurs, if a change occurs that causes Q to become less than K, then the equilibrium position will shift toward the products from left to right until Q equals K again, and equilibrium has been reestablished. If instead the change occurs that causes Q for some reason to become greater than K, then the equilibrium position will shift toward the reactants from right to left until eventually equilibrium has been reestablished and Q equals K again. So here are a variety of stresses that we'll talk about. So the first category is changes in concentration. What happens if I add more reactants? Well, if additional NO2 is added to the reaction vessel, and we're going to do all of this at constant temperature, my concentration of NO2 is going to increase. And so I'm showing that by, you can see on my little graphic here. So I have an increased amount of the NO2 as indicated by this larger font. At this point, Q would become less than K. So the equilibrium position would shift toward the products if you add more reactants. Now, besides Q versus K, you could also use a kinetic argument. Remember that the more collisions you have, the faster the reaction rate. Well, if we increase the concentration of the reactant, there's going to be a greater number of collisions between reactant molecules, and the rate of the forward reaction would increase. Well, what about if we add more products? So if we add more products, now we're going to be adding additional N2O4. So what this is going to do with respect to our value of Q, Q will now become greater than K. So adding more products will cause a shift toward the left. And again, you could use a kinetic argument and say, well, we're going to increase the concentration of N2O4. There'll be a greater number of collisions between N2O4 molecules, and that will increase the rate of the reverse reaction. Besides adding more of a chemical, you also could remove a chemical. So if we take away some NO2, that will cause the value of Q to become greater than K. So effectively, we are decreasing the concentration of NO2, and the equilibrium will shift toward the left. If instead we take away some products, so now we cause the value of Q to become less than K, then the equilibrium will shift toward the right. So in terms of adding or removing chemicals, Le Chatelier's principle tells us that the system will eventually reach equilibrium by responding to that change, by trying to counteract that change. And Q versus K is a great way to think about this and justify your answer. So on the AP exam, do not say because of Le Chatelier's principle and then that's it. That is not a sufficient explanation. But if you said because as a result of this change, Q now becomes less than K, which will shift the equilibrium position toward the right, that is a satisfactory explanation. Okay, so if they talk about discuss your answer in terms of collisions, then I would mention that the rate of the reaction is increasing or decreasing. So just read the question carefully. But Le Chatelier's principle is a fine thing to discuss, but it cannot be a reason on its own. So be careful about that. Okay, another example would be, besides change in concentration, is a change in pressure. So one way to change the pressure is to heat up the mixture. Now, we're not going to talk about a change in temperature until later. So there are two ways to change the pressure. You can either add more of a gas, or you can change the volume of the container. Okay, so we're going to do this adding a gas, but we're going to add an inert gas such as helium or neon or argon. Now, is the total pressure going to go up? Absolutely. However, let's talk about Q versus K. Since helium or neon or argon are not featured in the equilibrium expression, then the concentration or the pressure of the individual chemicals, N2O4 and NO2, remain the same. So Q is still equal to K. There would not be any shift. So if you increase the pressure by adding a gas that does not participate in the chemical reaction at all, then the partial pressures and the concentrations of all of the gases that are involved in this reaction remain the same. So no change in the equilibrium position. Now, if we decrease the volume of the reaction vessel, well, that's going to increase the pressure of the gases. So for example, pretend that we have an equilibrium in which the concentration of N2O4 is 5 molar and the concentration of NO2 is 1 molar at equilibrium. So 5 divided by 1 squared is 5. What would happen to the concentration or partial pressure of each gas if the volume of the reaction vessel is reduced by half? So when you reduce the volume of a gas by half, according to Boyle's law, you double the pressure. So if I plug in new numbers for concentration, in this case, instead of 5 and 1, if I plug in 10 and 2, well, 10 divided by 2 squared, that's 2.5. So what happened is my value of Q is not equal to K. And hopefully you remember that when Q is less than K, equilibrium would shift toward the right. So we're going to shift toward the N2O4 if we reduce the volume of the reaction vessel in this case. What if we increase the volume of the reaction vessel? Well, now that's going to cause the pressure or the concentration to go down. So if I double the volume of the reaction vessel, now my concentration of N2O4 becomes 2.5, and my concentration of NO2 becomes 0.5. If you plug in these new values into the expression, notice that 2.5 divided by 0.5 squared is actually 10. So our Q has changed. Our Q is now larger than K, so we're going to shift the equilibrium position toward the left. Here's a way of understanding what's going on here in terms of particles. So I've got 12 molecules in this particle diagram. And if you count, there are 1, 2, 3, 4, 5, 6 molecules of NO2, and there are 6 molecules of N2O4. So in this particle diagram, what happens when I decrease the volume of the reaction vessel? Well, those 12 particles are now occupying a smaller space, so the pressure goes up. So which side of the equation, the left or the right, will this equilibrium shift has to do with a way of counteracting this change. So how can the total pressure decrease slightly? We have to reduce the number of molecules of gas in the container. So when you decrease the volume of the reaction vessel, you're going to shift to whichever side of the reaction has fewer moles of gas. So what I've done in my final particle picture is I now have only 2 molecules of NO2, and I have 8 molecules of N2O4. That's a total of 10 molecules. So I have reduced the total number of molecules in the container, and that is because the equilibrium is trying to respond to this stress by decreasing the total pressure. Equilibrium shifts toward the side of the reaction with fewer moles of gas. Okay, what about if we increase the volume of the reaction vessel? So I've got these 12 molecules again, 6 of NO2 and 6 of N2O4. I'm going to increase the volume. So now the pressure has gone down. So the volume has increased, the pressure goes down. So how can the pressure increase slightly? Well, the reaction would have to shift toward whichever side has a greater number of molecules. So what I've done now is I have decreased the amount of N2O4, and I have increased the amount of NO2. So I have increased the total number of molecules. Again, what happens when you increase the volume of the reaction vessel is equilibrium will shift toward the side of the reaction with more moles of gas as a way to sort of counteract the change and increase the total pressure. So you can use Q versus K, or you can use this particle diagram to help you understand what's happening inside the reaction vessel. Okay, so again, decreasing the volume of the reaction vessel causes a shift toward the side of the equation with fewer moles of gas. Increasing the volume of the reaction vessel causes a shift toward the side of the equation with more moles of gas. What about this? Take a look at this equilibrium system. We have 2 moles of gas on the left, and we have 2 moles of gas on the right. So what do you think is going to happen if we have the same number of moles of gas on each side of the equation? Changing the volume of the reaction vessel for a system like this would not cause a shift at all. Why? Because each side of the reaction has the same number of moles of gas. Now let me show you the Q versus K. Suppose, I'm just making up some numbers right now, I have the equilibrium system, HI squared divided by H2 and I2. I'm just going to plug in some numbers. So 5 for the concentration of HI, and then 1 for the concentration of H2 and I2. Now 5 squared divided by 1 squared is 25. What happens if I double the concentration of each chemical? Well, 5 becomes 10, and 1 becomes 2. But 10 squared, which is 100, divided by the product of 2 times 2, that's 4, it's still 25. So there's not going to be a shift because Q is still equal to K for this particular system. All right, so I talked about change in concentration and change in pressure. I now want to talk about change in temperature. Again, we go back to the NO2 and N2O4 system. Remember that if it is brown, it's going to have more NO2. And if it's lighter shade of brown or getting closer to colorless, it's going to be more of the N2O4. What happens when we place this reaction vessel that contains a certain equilibrium amount of each gas into a hot water bath? So we're talking about changes in temperature. Well, if we do that, it turns darker brown. And if we put it in an ice bath, the color actually fades and it gets lighter. So I'll show you a short video of this.
We start this experiment with 3 tubes containing red-brown NO2 and colorless N2O4 in equilibrium. First, one tube is placed in hot water. A second tube is placed in cold ice water. After a few moments, we note that the tube in hot water has darkened in color. It now contains more brown NO2 than the tube which we kept at room temperature. The tube in ice water has less brown NO2 in it. It is much paler because the equilibrium has shifted to favor the formation of colorless N2O4.
So it's a great example of an experiment that we now have to draw some conclusions about this reaction. So increasing the temperature was a shift toward the brown NO2, and decreasing the temperature was a shift toward the colorless N2O4. So these observations can tell us information about this reaction. Is this reaction, which is as written, endothermic or exothermic? I'm going to give you another piece of data. For this reaction as written, the value of K is 160 at 15 degrees Celsius. And the value of K is 5 at 100 degrees Celsius. So changing the temperature will also change the value of K. We saw this with kinetics, with reaction rates, that the value of K, the rate constant, will change when you run the experiment at a higher or a lower temperature. Otherwise, if you're just changing pressure or concentration or adding or removing a chemical, and if you're not changing the temperature, then the value of K will stay the same. But here we are changing the temperature. So what does going from 160 to 5, as far as the equilibrium constant, what does that tell us about this reaction? Is this reaction endothermic or exothermic? Well, if we decrease the value of K, that implies that we have less products or more reactants. So it is a shift toward the left. And that happened when we increase the temperature. You can think of increasing the temperature like you're adding heat. So it indicates we have an exothermic reaction in this particular case, because when you increase the temperature, the reaction will shift in the endothermic direction, essentially to consume some of the heat that was added. So it's a way, according to Le Chatelier's principle, of counteracting the stress. So let me talk about this. We have an endothermic reaction at the top of the screen, and we have an exothermic reaction at the bottom of the screen. So for an endothermic reaction, if you increase the temperature, it's like you're adding more heat. It will shift toward the right, and K increases. If you have an endothermic reaction, but you decrease the temperature, it is like you are removing heat. So the response to that would be the system would shift toward the left to kind of produce more heat as a result of that change, and K decreases. On the other side, if you have an exothermic reaction, increasing the temperature is like you're adding more heat. So it's going to consume some of that heat and shift back toward the left, and K decreases. And if you lower the temperature of an exothermic reaction, it will shift toward the right. So again, these are the kinds of statements you can make to justify your answer. If they indicate, justify your answer with respect to T, you can't really do Q versus K. It doesn't work in that case, but you can say that increasing the temperature will shift the reaction in the endothermic direction, and decreasing the temperature will shift the reaction in the exothermic direction. So in our situation, for the NO2 reacting to produce N2O4, when they placed it in the hot water bath, it turned brown because it was shifting toward the brown NO2. And when they placed it in the ice water bath, it was shifting toward the colorless N2O4. So when they raise the temperature, the value of K decreases, indicating a shift toward the left. That confirms that we have an exothermic reaction as written. All right, I want to talk about particle diagrams one more time, just briefly. I found this question on AP Classroom, and I thought it was very relevant to today's lesson. Now you can see we have 3 different chemicals in the box on the left. We have PCl5, which looks like this. We have some PCl3, which looks like this. And we have some Cl2. Now, if you count, you're going to notice that we have exactly 3 of each kind of molecule in the box in this very simple particle diagram. What they have done is they've done a volume change. We still have a total of 9 molecules in the box, but the pressure has gone up. So in which direction are we going to shift the equilibrium? So immediately after the volume change, there's been an increase in pressure. Remember that you have to alleviate that stress by shifting toward the side of the reaction that has fewer moles of gas. So if you were asked to draw the particle diagram, once equilibrium has been established, you would need to have not just 3 molecules of PCl5, but at least 1 more. And that's what I've done here. I could have drawn 2 more, but I was kind of getting crowded in this little box. So I have drawn an extra PCl5. Now, because the reaction has shifted toward the right, there should be 1 fewer molecule of PCl3 and Cl2. And that's what I've done. So instead of drawing 3 molecules of PCl3, I have drawn only 2. And instead of drawing 3 molecules of Cl2, I've drawn only 2. So the total number of molecules is actually less. Instead of 9 molecules, we now have 8. And again, that was intended to show that there's been a shift toward the side of the equation with fewer moles of gas as a way of alleviating that stress of the increased pressure. All right, so we have talked about R.I.C.E tables, calculating equilibrium concentrations. We talked about the reaction quotient, Q, Le Chatelier's principle involving changes in concentration, pressure, and temperature, and again, a good look at a variety of particle diagrams today. So for your homework, again, we're still talking about equilibrium tomorrow, but for your homework, I have picked some equilibrium questions that are relevant to today's lesson. So this is the first screenshot. If you want to pause the video, you can do that. We're talking about an equilibrium between calcium carbonate and calcium oxide and carbon dioxide, and there is data given to you. And we're going to be answering parts A, B, C, and D. So again, if you want to pause the video or take a screenshot. And then I have a second AP practice question for you, also dealing with equilibrium. And this is the entire question. It was one of the short free response questions from an AP exam. So parts A and B, and that's it. All right, so tomorrow we'll go over the answers to these questions and we'll wrap up our discussion of Unit 7, equilibrium. So remember that there are helpful chemistry resources in the link in the video description. Again, this has been Michael Faribaugh from Albemarle High School in Charlottesville, Virginia. Remember that the deadline is this Friday, April 24th. So again, they are working, the College Board is working on solutions to help students get what they need to show their best work on these online AP exams. So if you need mobile tools or connectivity or know someone who does, go to cb.org/tech. All right, well, thank you very much for watching. Have a good day.